Hello again. So you're watching part 2 of the flow over an airfoil using Ansys Fluent 14. So now basically we have created this pressure far field and the airfoil wall. I have actually saved it. So we are going to make some changes in here. We are basically going to delete these two name selections. And we'll be making it as if it is an wind tunnel analysis. So this will be acting as your inlet and this will be your outlet. So we select this edge, this one and this one, right click, name selection, inlet. Remember, Fluent is case sensitive. Not case, actually name sensitive. This will be the outlet. OUT. And this remaining part will be the wall. Go to right click, name selection, edge selection, 1, 2, 3, 4. So we have this name selections and also the mesh. As you can see here, we have already created the mesh which I have shown in the part 1 of this video. So the airfoil name selection is done. Now we will go to 5, save project. Update this project. If you have this icon in here, you always update the project. So the mesh is done. Now as it is an airfoil, we will be needing double precision. Okay. Now we'll be solving a pressure base because it is not compressible flow. Steady will be doing it. We'll go to models. Energy equation will be off. We'll be doing for 1 meter per second, which is essentially laminar, highly viscous flow. So we'll be setting it as laminar, and materials we'll be selecting it as air. Created it. Okay. And then subzone condition we don't need it. We need boundary conditions. Inlet, velocity inlet, edit. Now it shouldn't be normal to the boundary. You have to change it. If it is normal to the boundary, it will be along this direction, along this direction, along this direction. So we don't want along this direction. We want it along the x direction, that is this direction. So what we'll do it, you can either choose for magnitude and the direction, where this is the magnitude and this is the flow direction, that is the cos theta and the sin theta values. I mean cos alpha and sin alpha values, where alpha is the angle of attack. And either you can have a components, that is, this is actually V cos alpha, this is V sin alpha. So we'll be, instead of components, we'll be going for magnitude and direction. Now let me set this magnitude as 1 meter per second, and the flow direction is along x-axis, that is that is alpha is equal to 0, 0 angle of attack. Okay, this outlet would be pressure outlet, this wall, airfoil wall is stationary, no slip condition. Okay, the other wall is headed, we give this as a slip condition, everything remains 0. Now we go for reference values, refer from inlet, solution methods, monitors. We go for this drag, print and console, airfoil wall. We need the drag around the airfoil, so we'll select this airfoil wall. Okay, lift, okay, moment, not the wall, it's only the airfoil. We need it around the airfoil. Okay, and then solution initialization, standard initialization, go from the inlet, initialize. Run calculation, 500 iterations, calculate. This is in the screen you are looking for CD versus iterations. So we'll wait for the solution to converge. So now we see the 99th solution has converged. So okay, we go for graphics and animation, contour, setup, filled, display. So it is not displaying because you have to select this. Okay, contour your pressure, static pressure. So this was the static pressure, total pressure, display. So this is how exactly your total pressure is. Wow, this is actually amazing. This is how exactly your total pressure is varying. Velocity, magnitude, display. This is how exactly your velocity is varying at 1 meter per second. Vectors, setup, display. So you have vectors also in this case. So you see how exactly the flow is turning. Now you can also see the path lines if you want. So this is around the airfoil. This is now the interior surface body. So the path line is see, you can see the streamlinedness. It's wonderful. You see how exactly it is going. There is hardly any pore separation at this point. Yeah. This is path line by particle ID. Reports. Now let's check calculation. So now we will solve for an angle of a certain angle of attack. So now we'll go to boundary conditions, inlet. So we'll keep the velocity magnitude as 1 meter per second. We will change the flow direction. So before that I need to calculate the value. So let us take alpha as 4 degree. So cos of 4 is, sorry, it's not 0. So cos of 4 is 0.9975 9975. And sin 4 is 0.697 0.6975 0.06975. So this is sin and cos alpha value. So this basically is the equation. So what we have done is we have taken a triangle. So the hypotenuse is the velocity which is acting along this direction, that is alpha equal to 4 degrees. So the cos, so the x is the cos component, cos alpha, and y is the sin component, and the velocity magnitude we have kept it same. If we use this option as components, we have to, for the x velocity we have to take v into cos of alpha, and for the y velocity you have to take v into the sin of alpha. So in this the velocity magnitude is separate, so we will keep it separate, and we will just specify the direction, the flow direction. We will click OK, and the rest remaining the same as pressure outlet, airfoil hole as a slip condition. Okay, so airfoil hole is no slip condition. We give it as a slip condition. Okay, so the reference values again will be from the inlet. Solution method is the same. Monitors will be monitoring CD, CM, CL in this case also. Solution initialization, compute from inlet, initialize. Okay, so you see this change. This is actually 1 into V into cos alpha, V into sin alpha. V is 1, so essentially it's the same value. Solution activity is 500. Calculate. So at alpha equal to 4 degree and velocity at equal to 1 meter per second, the solution has converged at 141. So click on OK. Graphics and animation, contours, setup, pressure, static pressure, field, display. Okay, you can see here the static pressure, how exactly it is varying. If you have this problem, if you have it is going beyond it, make a bigger domain. That's the only solution. So this is how exactly the absolute pressure is varying. Not absolute pressure, total pressure. So if it is not getting fitted in the boundary layer, you just change it. This is how exactly your velocity is varying. So this was the contours. Now we go for reports, forces, setup, forces over the airfoil in X direction. So we have the drag force over it. This is your drag force. The total drag over at alpha equal to 4 degrees. Now we change it to y to 0 and 1. So this is 0 F1 0. This is your lift force. This is your lift force. You can have coefficient of pressure, everything. Now we go to plots, XY plot, setup. You can have static pressure versus the direction vector on the surface of the airfoil wall plot. So this is how exactly the static pressure is varying over the airfoil. You can see this pressure difference, static pressure difference, and here this is the main reason for lift production. Total pressure and display. So this is your total pressure variation. Instead of direction vector, you can have this curve length also. So this curve length is from here to here, or it will be from here to here. You have the starting point and the ending point over here, plot direction, and the direction vector. And the direction vector is this: the upper surface, the lower surface, and along the X direction. So this was about the pressure. You can have velocity also. So velocity is pretty uniform. It's mostly condition. It's actually 0. So this was all about the flow over an airfoil. You studied how exactly to create a structured mesh in part 1, and part 2 we basically saw how exactly we have to solve it. In real cases, you will take what exactly the flow physics is. Accordingly you will go to models, select what exactly you need energy equation or not. In most cases you don't need energy equation. You will see in this flow, if the flow or you have any turbulence modulus as volatile RMS, the epsilon, T, omega. These are basically all turbulence modeling, and any other equation for that matter. So materials, we will be selecting materials. For air itself we have number of options. Say for density we have, instead of density we have ideal gas, incompressible ideal gas, real gas in different form, bucinic, piecewise linear, piecewise polynomial, everything. It depends upon your flow physics. So better study the flow physics first before doing the CFD analysis. That would be my particular genuine advice to you. So thank you for watching this video. I hope you enjoyed it. My name is Pawan Mehta. Please, if you have any queries, please contact me. Thank you.